Hello everybody, my name is Jeff Bees and I'm here to talk to you about the Thermal Radiation Lab for ME 4031W Basic Mechanical Measurements Lab. So as a walkthrough of what we're going to talk about in this video, we'll start out with the experimental setup, paying particular attention to the thermopile, Stefan-Boltzmann lamp, Leslie's radiation cube, and infrared thermometer. Then we'll go into the procedure, which is broken up into three components: the inverse square law, and then the emissivity measured both by the thermopile and the infrared thermometer. And then finally we'll wrap up with a talk about what deliverables are expected from this experiment. So to start out with the experimental setup, here's what you'll see when you come into the lab, and here's a schematic of the same setup. One of the features of this setup is the dashed lines that we can see around the thermopile and leading between the Stefan-Boltzmann lamp to the power supply. And these correspond to the inverse square law configuration, where the thermopile is facing the Stefan-Boltzmann lamp, which sends the power readings to the power meter, which digitizes that reading and sends it to the computer through a USB port. The power supply sends a current directly to the Stefan-Boltzmann lamp in order to turn it on. Meanwhile, the Stefan-Boltzmann lamp is attached to an adjustable track where you can adjust its position left and right in order to change the distance between the thermopile and the Stefan-Boltzmann lamp, given by L. This is done in order to explore the inverse square law. For the next part of the experiment, the thermopile is rotated 180 degrees so that it is facing the radiation cube, which allows the thermopile to read the radiative power emitted from each surface based upon the emissivity of each unique surface, while the radiation cube is heating. Meanwhile, there is a thermistor embedded at the base of the radiation cube. The thermistor is plugged into the voltage divider box, which has a 5-volt power supply and outputs leading to the DAC, which then sends the thermistor readings to the computer, again through USB port. An important note about the radiation cube is that during the heating process, each of the 4 surfaces is assumed to have the same temperature at any given instant. For the final part of the experiment, the infrared thermometer is used by pointing it at each of the surfaces in order to read the temperature while iterating through the user-controlled emissivity parameter on the thermometer. This temperature is then compared to the thermistor reading provided by the LabVIEW program until the correct emissivity creates a matching temperature. Now, the way a thermopile measures this radiative power is through a series of thermocouples that creates an area over which the power readings are measured. An important feature about the thermopile is that it can actually rotate from one position to the next, and that will involve pointing it towards the Stefan-Boltzmann lamp during the inverse square law procedure, and then the radiation cube during the emissivity procedure. In order to do this, you'll want to loosen the set screw and then raise the thermopile, rotate it around 180 degrees, and then lower it back into the base and reset the screw. The power meter then digitizes these thermopile readings by taking the input through the detection port and then outputs those readings to the computer through the USB plug. An important part about operating LabVIEW with the power meter is that it requires the 32-bit version of LabVIEW, not the 64-bit. If you use the 64-bit version, it will produce null readings due to the compatibility of the power meter itself. Another note about it is that it will provide readings on the display here. However, the resolution of the display is rather poor with 1 milliwatt resolution. However, a finer resolution of information is sent to the LabVIEW program, and therefore you don't have to worry about this particular resolution issue. The Stefan-Boltzmann lamp can be powered by connecting the positive and negative ports directly to the corresponding outputs of the power supply. And then you'll want to adjust the power supply setting so that the voltage is no higher than 13 volts, while the current is between 2 and 3 amps. You'll then want to take these settings and calculate the power output of the Stefan-Boltzmann lamp. In order to investigate the inverse square law, we have an adjustable track which allows you to change the distance between the thermopile and the Stefan-Boltzmann lamp. The position on the adjustable track can be determined using the position indicators located at the bottom left of the thermopile and Stefan-Boltzmann lamp. The point on the position indicator represents the effective location of each device. You'll want to keep the thermopile fixed at 90 millimeters while changing the Stefan-Boltzmann lamp's position, and therefore the distance, using spacing given by the inverse square law. In order to do this, you'll want to determine the maximum and minimum distance from the Stefan-Boltzmann lamp. Take the inverse square of each of these points, and then increment 12 points evenly between those extremes, including the extremes. Once you've defined these points, you will convert them back over to distance using the inverse square root of those values. The Leslie's radiation cube has a number of important features. It has 4 thick aluminum walls, and each of those 4 walls has a different surface condition. Those conditions are black, white, polished, and dull. In order to change the surface that is being measured by the thermopile, you'll want to use these knobs located at the base of the cube in order to rotate that cube. Be very careful not to touch the rest of the cube while it's heating, because it can get really hot and cause burns. Now, the source of the heating is a 100-watt light bulb that is located at the center of the cube region underneath the lid. And you'll want to keep this lid on it during the course of the experiment so that heat does not escape as readily. And then you'll want to use this dial in order to set it at the highest setting, and then toggle the on-off switch to the on position, therefore heating the radiation cube. In order to measure the temperature of each of these surfaces, there is a thermistor located at the base of the cube, and the output plugs of the radiation cube can be plugged into a voltage divider box, given here, with the thermistor terminal ports located on this side, while a 5-volt DC power supply is plugged in here, and then the outputs of the circuit go to the DAC. Now, important discrepancy on the voltage divider is that it labels the black port as the ground of the DC power supply, when actually you should use the negative port. The infrared thermometer measures the temperature of a surface by measuring the energy level of the infrared radiation being emitted from that surface. And in order to do that, you need to plug in an emissivity in order for the calculations to be performed. Another important part about its measurement acquisition, it actually averages over a circular area, which are indicated by 2 laser points, marking 2 edges of that circle. This area changes based upon the distance that you're measuring from, as indicated here. Sometimes the lasers can actually be deactivated. In order to adjust the activation status of the lasers, you want to hold down the down CF button, meanwhile pulling the trigger for at least 1 second simultaneously. So you can use this infrared thermometer in order to determine the emissivity of a surface. And the way you can do that is to adjust the emissivity that the infrared thermometer is used in its temperature calculation until the temperature measured by the infrared thermometer matches the known temperature given by the LabVIEW software. In order to adjust the emissivity, you'll want to press the mode button until you see the down arrow, up arrow, E icon appear on the screen. Then you'll want to use the down and up arrows in order to adjust that emissivity value. Now, the lasers that are emitted from the infrared thermometer is a class 2 laser. It's on the lower category of lasers. However, if you stare directly into the beam, it can cause flash blindness, which, while temporary, is not good, and therefore should be avoided. Now we'll move on to the procedure. Now, for the inverse square law procedure, I will use a video to guide the procedural steps. Now, the first step will be to turn on the power meter. And then you'll want to select the Start button, type in LabVIEW, and search through the results in order to find the 32-bit version, not the 64-bit version, because again, that will result in null readings. Then you'll want to click on the Open Existing, and select the Radiation Lab folder, and then select the Radiation Lab program. Once it shows up, you'll want to initialize the DAC, making sure the device is correctly selected. Select a file path. Once you've selected the file path, you want to make sure that the thermopile is pointed towards the Stefan-Boltzmann lamp. Plug in the power supply to the Stefan-Boltzmann lamp and set the power level to less than 13 volts and between 2 to 3 amps. Record this power. You can leave the number of samples and sampling rate at 1,000, and then you'll want to click Run. Now, as it's operating, you'll first notice that the temperature reading is not showing up, and the thermistor probe is also giving null readings. That's because the thermistor is not plugged in. Meanwhile, the thermopile is, and it's producing a power reading that's declining right now, and we'll want to wait until a steady state reading is established. Once it appears as though you've reached a steady state reading, you'll want to set the distance between the thermopile and the Stefan-Boltzmann lamp, and you'll start out with the furthest distance available, and then make sure that the Stefan-Boltzmann lamp is selected before acquiring that data point. Then you'll move on to the next position and plug that value into the control here. And when you move the Stefan-Boltzmann lamp to the new position, you should see a dramatic spike in the power levels, and that power level will actually overshoot your final reading before coming back down. Now, once it appears as though the steady state value has been reached, which you can determine using the thermopile graph, you are now okay to acquire that next data point. And so you can click on the Acquire button. And then you'll plug in the third distance value, which, as you can see, does not create a linear trend between the first and second data point. And once you move the Stefan-Boltzmann lamp to the new position, you should see the reason why we're using the inverse square law, and that is because the change in power between the first and second data point should be roughly the same as the change in power between the second and third point, and so on. And so you will continue this process going through each of the 12 locations, acquiring each data point once a steady state position has been achieved. The second part of the experiment continues to use the same program. However, now you'll want to point the thermopile towards the radiation cube, starting with the black surface facing the thermopile. Make sure the cube is plugged in and hook up the voltage divider box to the power supply with a 5-volt source. Also plug it into the DAC and the radiation cube. And then select a new file path and change the surface setting to black, noting that the distance is no longer relevant since it is only present for the inverse square law. Then we can run the program. Now we want to do this before we turn on the radiation cube, and that is to make sure that the thermistor is reading proper values and is roughly located at the ambient temperature. Then, with the lid on and the cube set to high, you can turn it on, and you should see the temperature and the power begin to rise. Now, once it appears as though the power is increasing with a linear trend, you can click Acquire, and then move on to the next surface. And then you can rotate that surface by using the knobs, and then you should notice a change in the power reading, which will have a transient phase before eventually leveling off to a new slope. Now, the first few measurements will be a little difficult to get just because you're at a really small power level and the slope is less defined. Once it looks like it's leveled off, you can acquire that data point, move on to the white surface, and then onto the dull surface, checking to make sure that the slope is constant before taking that next data point. And as you move on to later measurements, the trends will become more clear, and you'll start to see 4 distinct slopes generated from your transitioning. while the white and black surface have roughly the same slope. The polished surface has a very small slope, and the dull surface has kind of an intermediate value. You'll want to continue this process until you reach roughly 100 degrees Celsius, and make sure to at least get 6 to 7 data points, though more data is better due to statistical significance. Once you've completed part 2 of the experiment, you can select a new file path and then click Run on the LabVIEW program while making sure that the on-off switch to the radiation cube is switched off, which means that the lamp is no longer heating the cube. This will allow you to watch as the temperature decreases during the cooling process. An important thing to keep in mind is that the indicator here will give you a numeric reading, which you can then compare to the reading from the infrared thermometer. Then you'll use the infrared thermometer to adjust the emissivity given on the thermometer until the temperature reading on the thermometer matches that of the indicator on the LabVIEW program. You'll want to make sure that the laser is on and traces a circle that maximizes the area on the surface while still being within the bounds of that surface in order to get the highest sampling of the area. Once you've matched the temperature of that surface to what's provided by the LabVIEW program, you'll move on to the next surface and adjust the emissivity until the temperatures match again, making sure to record each of the emissivities indicated by the infrared thermometer. Once you've finished this process, you can stop the program. Before you're done, you'll want to make sure to measure the dimensions. You'll want to make sure to measure the dimensions of the cube and the thermopile for view factor calculations later. Now we'll move on to the deliverable results. There are 3 primary results to this experiment. The first one being a plot of the inverse square law, which is power versus distance. If you use the rules of logarithms, you can plot this in such a way that a linear trend can be seen, with the slope indicating the power relationship between the radiation power and the distance. And then you can perform linear regression on your results in order to compare the experimental slope with the expectation, recalling that since the power measured by the thermopile is a function of the view factor, which for our system can be approximated by the inverse square law with a proportionality with L to the power of -2, resulting in a slope of -2. The second result is a plot of the thermopile power versus the temperature. And you'll want to plot this also in such a way that a linear trend can be seen between the radiative power and the temperature. And you'll want to make sure to include all 4 surfaces on the same plot. A guide for this plotting can be given by this equation here, where the power is a function of 2 constants, the emissivity of that surface, the Stefan-Boltzmann constant, and the measured temperature to the 4th power. The last result will be a table summarizing the emissivity values that you calculated from part 2 and 3, as well as a corrected emissivity for each surface based upon the highest surface emissivity, recognizing that the definition of emissivity is given by the heat flux of one surface with respect to that of a black body. That's all I have for you, so I hope that you have found this useful and that you have a wonderful day.